Hey everyone and welcome back. This was BSidesSF CTF 2024. Overall, very fun CTF. There are still 24 hours left in the competition, but there's another CTF tomorrow, and I think I might try to touch grass this weekend, so I'm calling it quits a little bit early. But overall, the challenges were pretty fun. I think there was one challenge that was maybe the difficulty was a little bit off, but for the rest of them, I thought they were good difficulty curve. I think they said something like 40 or 50 challenges are going to be released, so pretty big CTF, which is just a lot of challenges. But like I said, had a good time, and I'll be covering these 18 challenges. So timestamp should be below somewhere, and yeah, let's get started. The first crypto challenge is missing characters. It says, can you read between the lines? The flag is in this format, and the author was Anch. So for this challenge, we're just given this text file called ciphertext. We can see it is an array of arrays of integers. If we run length on the top level array to see how many child arrays there are, it comes out to like 23 or 28 or something like that. And if we do a length on one of the inside arrays, it was either 254 or 255. And from there, we can probably guess what we're supposed to be doing. So the title of this challenge was missing characters. And so presumably for each of these inside arrays, we're supposed to figure out the missing number, and that corresponds to the characters of the flag. So that's what I did. So I wrote a little Python script. Ciphertext.py. I defined the array of arrays called groups. And then for each of those groups, I'm going to generate the set of all numbers, or all character numbers, ASCII numbers, although all character numbers. And then I'm going to take the set difference, so all the characters minus all the numbers in one of those arrays. And the remaining should just have a size of 1, and it should be the flag character. And then I convert that character into a character and append it to the flag variable, and that was it. So Python 3, I think it was called ciphertext, yeah. And we get the answer, CTF read between the lines. I'm going to cover Shinji as part of reversing. So the next crypto challenge is opnukeagi. It says, comrade, you're our last chance to stop the AGI. If your mission to infiltrate the nuclear missile silo fails, all hope will be lost. The author was symmetric. We're given a netcat port and a download file. So for this, the challenge was a little bit involved. It was, once you know what to do, it wasn't too bad, but basically we netcat to this port. There's some Russian text. There's ASCII art of a missile, some more Russian text, looks like a timestamp, and then it asks us a question. Cool. Then we're also in the download file, we're given this mission.txt. This says something about we just need to hack into the silo. I don't think it said anything too important. And then we're given this movie. It does load. And in the movie, we can hit play. There's a couple things to point out. So the timestamp is incrementing each second. Nothing on the screen changes except for, as part of this dashboard, except for this 8x8 grid of numbers. And then at the very bottom, if the thing would go away, there we go. Well, that kind of works. We can see at the bottom, I can't really point, but you can see kind of near the middle, there's that KOD symbol. That's Russian for code, and then we're given some sort of hash. Thankfully, my wife can read Russian, so she was able to decrypt most of this. Thankfully, none of this really matters. Basically, it's just asking us for this code. You can see it's the same color, or sorry, the same letters, that's COD and COD. So we need to find the code corresponding to this timestamp. And so that's what the challenge was. And so what's happening is this timestamp, every second, starting from 1984, we need to generate a timestamp for 2024, so way in the future. But 1984, these numbers are switching, and somehow these numbers correspond to the code. And we need to like fast forward whatever is happening here to current time. Once we figured it out, we just take the code and we put it into the terminal and we get the flag. So the trick was figuring out what this thing is doing. If you just stare at this for a bit, just every second it clicks, you'll kind of see that it's actually, all the characters are just shifting left. And so you can see this one, it's going left, left, left. And so that's most of it. And then there's one other thing that happens. When this topmost character here slides off the screen, what happens is this row right here and this row right here are XORed by their own bytes. And so that's pretty much the pattern that you kind of had to reverse. By default, every second it shifts to the left. And then when a 1 shifts off only on this top one, this row and this row, or I guess column, this column and this column are XORed by some integer mass that you just have to play with to see. And that was the challenge. So once you know what the pattern is, you start from 1984, whatever timestamp this is, and you let it play forward all the way to 2024. and then you type in the code. So the solve for me looked like this. So I took one starting time from the video, which was this time. I wrote it out in binary, got rid of all the new lines, and then I converted all those binary digits into just binary integers. The program takes like 20-30 minutes to run, so a lot of it was just getting rid of strings, converting everything to integers, so it would be just a little bit faster. I wrote a function to convert it to code. Oh, and so part of the video that I didn't talk about, how to get there? Back to the video, is somehow we had to figure out how it computed the code. I think it was just straight down. So if you look at, or maybe it was across, sorry, it was across. So if you just take this integer and then convert it to hex, it is 04. It's a little hard to see, but 04. And if you take this, this is 88 in hex. And you can also see, so this would be 1, 2, 4, 8. So 8, 8. So then 0, 0, 0, 0, 0, 0, 0. This would be another 8, 1, 0, 0, 0, 0, 0. And we can see 8, 1, 0, 0, 0. So all you had to do is just read the integers across. So it's shifting that way. And then when you want the code, you read the integers across. Cool, so I have a little toCode function. I just test to make sure it works. So I take my current code, make sure it produces the right thing. We're good. Then I wrote a little rotate function. Like I said, this is just going to push all the arrays to the left. I guess I didn't quite specify, but also when the very top one, when it pushes off is special, but for the rest of them, they just wrap. So this one would wrap to here. And so pretty much you can just think of this as a long 64-bit long string. And then, so that's what I do. I just pop off the first one and then I add a 0 to the very end. These are those two masks I was talking about. Some of the columns, when you have a 1 pop off the end, you just need to XOR the mask with that row. So really just do an XOR. So it was column 3 and column 7. You just do the XOR there. And then you return back the binary string. I had a little function for dumping it so I could print it out to inspect it. And then I just ran from the starting time all the way to a nearby time. So when I was doing this challenge, it was around this time. And I just keep rotating. Like I said, it takes like 20 minutes or something. It definitely takes a while to get near current time. Once you're near current time, you can do something else. And yeah, if you're not familiar with this tool, TQDM, it's super cool. I'm not going to run it to the current time, but you can see, oh, well, it's too fast. Let me start from the beginning. This is how you generate those progress bars. You've probably seen this before, but if you're ever running a script, instead of having to print out like I mod 1,000,000 or something, you can wrap it in a TQDM. And we can see that, the script took 20 minutes the first time I ran it to go from the beginning to the very end. And so it's just a nice little progress bar, and you can see how many iterations you're doing per second. And all you have to do is wrap a range. It has a bunch of different options, this package, but all you do is just wrap the range and it generates the progress bar for you. Pretty cool tool. But anyways, once we get to the current time, I dumped out the binary blob, I printed out the current code, and then I exit. And that was it. And so then I'm not going to solve it again, but basically you just open up. Actually, we could. Let's just do it real quick. We have to do it a little bit fast though. Python CTF. This is BSides crypto. It was AG opnuke. Cool. Then we need to netcat. So this is going to give us. Oh, I need to convert these back. So I let it run to a nearby timestamp, and this is the nearby timestamp. You can see this one's much later. Let me cancel this. We run it. I think we have to be within like 30 seconds, so that's why I'm just canceling it. And we go to here. We're going to go to this timestamp. Now let's run it. This is the code we get out, and we place it here. And that was it. So, don't know what this says, but it looks like a big explosion, and it says Comrade AGI kaput. So, yeah, pretty fun challenge. The first forensics challenge was Doctor. It says this doc seems to be hiding something. Can you find out what's hidden? And we're given a .docx file, a super secret Word doc. So if you didn't already know, doc files are just zip files, so you can just unzip it. So we do an unzip super secret doc. I'll just replace it all because I already unzipped it. We can see already that there's some image files, which looks pretty interesting. So if we open those up, we go to the first image, and we already have the flag, CTF stock cute pics. So fun. The next three challenges in the forensic category were SGAI 1, 2, and 3. For these challenges, we're just given a single image. The image is an SGI image. I wasn't familiar with that format, but apparently it's called a Silicon Graphics image. and it's just a bitmap image. It really wasn't too complex of an image format. But anyways, there are 4 flags hidden in this image. And so I only found 3 of them. But this is what the image looked like. It kind of looks like a little Terminator sort of guy. The first flag was just running strings. So strings on sgi.sgi. And I think it was right at the very top, yeah. So the first flag was CTF, I name the flag. The flag 2, that's right. If you run hex dump on it, hex stop, hex sgi head. Actually, that's not true. If we take a step back, so you can look up the header format. I think it was on Wikipedia that I got it. So I took the hex dump, I copied it out, and I put it into here. And so we can see this is the SGI signature. We can see it's compressed. It's 8-bit. It is specifying it's an RGBA, or that's the pixel format. The width and height, blah, 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 reserve, max pixel. This was the original flag we got, but it also says the name field is like 80 characters or 50 characters or something. And so right after this name field, there's this data. And it doesn't really correspond to anything, and it's not part of the pixel data. I think it was still part of the name field. So what I did is I took that out, kind of compressed them, got rid of all the spaces, converted it from bytes, or unhexified it. Then I just played with the XOR keys. I think I did this in CyberChef first. We can actually do that. We'll take this, go to CyberChef. I placed it in here. They have a tool called XOR brute force. And so it's just going to brute force all of them. I was just guessing that was brute force. I don't know what else it would be. Oh, we need to do it from hex too. From hex, we'll put that at the top. And if you go all the way to the bottom, we can see this is mostly plain text. We can see a C, a T, and an F. And so we can see each one of these byte groups is mixed up. So if we take this, and we put this here, and we take this, we put this here, and we scroll all the way back down, we can see we have it correct. We just need to swap all those bytes. So I just did that in Python. You could probably do that in CyberChef, but I copied over to Python. So like I said, put it here, got rid of all the spaces, did a from hex, did the XOR. So we have the swapped flag. And then so for each grouping of 2, I just swapped those 2 characters and I print it out. So Python 3, flag 2. CTF pad, really do we need 512? So not sure what that's about, but that was flag 2. And then the last one, flag 3. Oh yeah, so for this one, we needed to separate all the individual channels. So we take in, we open the image. So this is using Python image library. I'm just dumping the pixels here. From here, I'm making 4 copies of the image so that I can separate the red, green, blue, and alpha. And then for each of the pixels, I just only save that 1 pixel or the 1 color for the pixel. So for each of the pixels, I'm going to get rid of the green and blue. And then I did that for alpha, but I've actually put alpha as blue. I did this in a different file too. And then I just saved, I think you can save all of them, but the flag is in each one of them, so it doesn't really matter which one you do. But if you save red.ping and you load it later, here's blue anyways. If you zoom in, you can see there's a flag here. And it says CTF invisibility cloak. The first misc challenge is crossworthy. It says solve the crossword in the program or attached as an HTML file and answer this question. What exploit technique can be found sliding down the puzzle in the circles? Flag is in the format, blah, 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 all lowercase, blah, blah, blah. Cool. So we download you can do the PNG or the HTML. I think the HTML is a lot easier. I already have a lot of it filled out, but basically you just go through and solve the crossword and you get the flag. So like I said, these are just the ones I only focus on the ones that are on the diagonal because that's all we really care about. And eventually you'll see nop, 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 nop. And so that's just a exploitation technique. It's called a nop sled. So if you have an arbitrary jump, nop means no operation. It doesn't do anything. So if you're going to jump somewhere in memory and you don't have an exact address of where you're jumping, you can just put in a whole bunch of nops. So if your instruction pointer points at one of these nops, it just slides all the way down. And then at the very bottom, you put your shellcode. But anyways, that technique is called a nop sled. So you put that in and you get the flag. The next challenge was llflagprinter. We've gotten the LLVM compilation started for you. Now you just need to complete it for your system. Author symmetric. For this, we're given a .bc file. I wasn't familiar with it, but turns out it's just a bytecode file for LLVM. And so all we have to do is finish compiling this program, and that's it. I installed LLVM. This is the command I used, apt-get installed LLVM. I let it run because it's like half a gig. Then you run LLC. Again, it's just found it online, llflagprinter.bc. This is going to generate a .o file, and from there we just need to finish compiling the .o file. So GCC. There's something about, actually I'll run it without this. So if you try generically, you'll get two different errors. The first is it doesn't like the relocation because position independent executable object. So we can either recompile this .bc with pi enabled, or we can just make it a static binary. So we're going to make it a static binary. And so that'll fix the first issue. So it's static. And then now there's some undefined references, first to cosine and also to round. These are math functions, so we just need to include libmath, so -lm, and it compiles. And so the output is a.out. We can run it and we get the flag. CTF LLVM, a LLM for V enthusiast. The next challenge is Shinji. It says, you will know when the time is right by It's Corgi 1, or It's Corgi. So for this challenge, we're given a APK, so an Android package file, I guess. So the first step is to decompile it. My decompiling wasn't working with Java for some reason, but there's online decompilers, so I ended up just using one of those. So www.decompiler.com, you just drag the APK over and it downloads it, it decompiles it into Java, and you get the output, and it just works. It's amazing, and it's free. You don't even have to make an account. So you get out the sources, you go down to main activity. So we find out that there is a flag display function, so we're on the right track. This function looks pretty long and complex, but really it's, if you write this out in Python, it's like 3 or 4 lines. I do like Java, just for some reason this seems overly verbose. What's going to happen is it's going to start generating a string. It's going to start with Shinji, and then it's going to append the current time. If the current time is not between these bounds, it's going to return an error that says like invalid time or something like that, I forget. It's going to take that string, so Shinji plus the current time. It's going to take the MD5 of it. Then this big while loop seems kind of complex, but all it's doing is it's converting that hash digest into a hex string. Then it's going to take the lowercase of it, and on that hex string, it's going to compute the SHA-1 of it. Then again, it's going to generate from the digest of SHA-1, it's going to compute the hex string. I think it converts it to lowercase again. And then after it's done that, it's going to compare against this value. And if it's true, it's going to generate the flag by just wrapping the timestamp with a CTF and a closing bracket. So really, we just need to write a script that takes all the times, all the seconds between this and this, prepend it with Shinji, and then do the MD5 and then the SHA-1 and see if it equals this hash. And if it does, we have the correct timestamp and we win. So I wrote a little Python script, solve.py. So I just copied out that function. So it's from here. We have the Shinji string. Here's the start and the end. Now I'm iterating through every single second. So I'm taking the MD5 of the Shinji and then the second. Like I said, there's so much code. I was copying it. I was implementing more, thinking I had to do more, but I realized I was just making things overly verbose. Then you take the SHA-1 of the MD5 string. Again, we convert it to lower, and then we just check to see if it's equal to that string, and if so, we have the correct second, and that was it. I forget how long this takes. Solve.py. Might take half an hour, so we're not going to wait. But anyways, you get out a timestamp and you wrap it in a flag, and yeah, that was it. So up next is pwn. So this is can't give in. It says, can you get shell? The binary has an executable stack and minimal hardening. The goal is RCE. The flag is located here. I don't think it said this when I was doing the CTF, but I could be wrong. I think this was added later. The author is Ron, and we're given a URL. We can take a look at it. Just ask for a password, and we're given a auth.cgi. So this challenge says it's a 101, which means a beginner challenge. I personally don't think it was a beginner challenge. I think it was a rather difficult first pwn challenge, specifically considering the other challenges that were in the 101 category. Also just based off of the solve count, only 21 people have solved it, and this challenge was open from the start, I think. We can see I got first blood too, which is fun. But like I said, I don't think it was a 101. I think there are things that could have been done to make it a 101, but I think in its current form, it wasn't quite a 101 challenge. But anyways, we're given that auth.cgi, so we can open that up in Ghidra. So anyways, taking a step back, CGI, forget what it stands for, but it's a way to run different programs from a web server. So normally we think of like web servers doing like Ruby or Python or Node.js or something like that, or PHP. But you can actually have the front-end service like Apache or Nginx use this framework called CGI to pretty much call any type of program. So like Bash or Perl or assembly or here, I guess, I mean, it's kind of assembly. We have a C++ program. I assume it's C++. Binary, and like I said, it just calls the binary. Apache calls the binary using this like CGI interface, and the program returns with HTML, and then Apache or whatever your web framework is returns that to the browser that made the request. So using CGI, you can pretty much put whatever you want on the other side. So in this case, we have a binary, so we can open it up in Ghidra. Pretty simple binary. It's going to return some text content. As part of the CGI framework, it passes a lot of the data through environment variables, and I think the body of the HTTP request is sent through standard in. So here we have a HTTP header, which is the content length. So we grab that out. I already renamed it to length. Then it's going to eventually read in from standard in into this set size buffer of 132 bytes, the length that we specified. So we have a pretty trivial buffer overflow. From there, it's going to compare the buffer to password is equal to my equal password to see if they match. If they do, it says success. Otherwise, it says error. Cool. So like the challenge description said, the goal is to get RSE. So like I said, we're not trying to pass in the password. We're trying to pass in something interesting exploitation-wise. And so I think the challenge was hinting that we're supposed to be pushing some shellcode, and then we jump to the shellcode. It didn't seem like an obvious way to jump to the shellcode. I was doing it for a little bit, and I think maybe you could do like an opslet or something and like just push it down really far and jump somewhere in the stack and just run it a couple of times, but that just didn't seem like that good of a solution. But I'm guessing that was the intended solution. But I'm also not really sure that would have worked. Could be wrong, but I was having a lot of trouble spawning shell. So I ended up doing something else instead. So I'll kind of talk my way through that. But anyways, to get started, I just treated the CGI program just like a normal binary, like we're doing a normal pwn challenge. We're going to ignore all the web server crap. So we just load in the binary, we spawn it like a normal process. Like I said, if we want to pass in variables, we're just going to use the environment variable argument. So content length is equal to 1,000. And in this case, this is just going to do a generic sort of ROP to spawn a shell. Normally, so if it was a binary, like a netcat, normally we need to write bin shell somewhere into process space. So if we look at the strings through here, I guess we should have looked to see if there were any interesting targets, but there's not much going on in the binary that's actually useful for us. I might have missed something, but I didn't see anything. There's no bin shell, there's no system call, there's no like backdoor or anything. Again, I could be missing something. So it seems like we need to be a little bit more clever. And so we need a way to write bin shell to somewhere in process space, and then we need to have the address of it so that we can then call the execve syscall and get shell. And just as a quick refresher, syscalls execve. This is what we're trying to do. So we're going to call, we need the syscall gadget. So somewhere we need to find a place where the instruction syscall exists. We need to set RAX equal to 59. We need, or OX3B, we need to set RDI equal to the thing we want to call, which in this case is bin shell or exec as, and then we're going to set RDX and is it RSI? Might have these mixed up, both equal to 0. It was RSI and RDX. So cool. So again, bin shell needs to exist somewhere. So if this was a normal binary, normally what we'd be doing if we were ROPing is we do a ROP and we'd read from standard in, standard out, standard air. So 0, LPSS. So this is just a known readable, writable segment within the process. And we'd read in 100 bytes. And so then that way we can just like, do a pwn dot send line, bin shell, blah, blah, blah. And it now exists, within memory at a known location. But like I said, this is going through some Apache web server to some CGI interface to the binary. So we don't really have like an interactive session with it, as far as I can tell. So we have to be a little bit more clever. And so one way to be clever about this is to use a write what where gadget. And so here, this is what one of those looks like. We are going to move the contents of RAX into the address of RDX. And so this is just like a little dereference. To find these, what you do is there's a tool called Ropper. So let me load that up real quick. You can do Python 3 module pip install Ropper. And so this will find all the ROP gadgets for you. And then you can do ropper file auth.cgi, no color. And this will, maybe there's no dash, no color, and this will dump them all out. Normally I pipe it to a gadgets.txt file, and then you just start looking for a gadget that allows you to write something to memory. So like I said, I found this one. And so what this is going to do is first I'm going to use pwn tools. So again, pwn tools, absolute magic. When you call pwn tools like this, ROP, and then just the arguments, it'll find the pop gadgets for you. So this is going to pop elf.bss into RDX and this string into RAX. We need to pad this to be 8 bytes. So again, pwn tool is amazing. It just finds the pop RDX and RAX for you. And so at this case, we are all set to call this gadget. So RX has bin shell, RDX has a known address. We call it and cool. So now at that address, we have bin shell. This is from what we were just talking about. And at this point, we populate all the gadgets so that we can then make the syscall. So execve bin shell 00, and then we call the syscall. Running locally as just a plain binary, this works. Everything's amazing. Great. Like I said, the trickiness is that we're running this over Apache. So again, we're making a web request to Apache. Our payload's in the post body, and somehow like we don't have a persistent connection. We can still use the TCP connection, but I just don't think it's actually being forwarded all the way through. Because I'll show that I'm able to call shell or spawn shell, but it's just not interactive. Again, I'm probably missing something, but I just had a lot of trouble with it. So I ended up moving to a further solution. But anyways, and I guess I'll just talk about the further solution, then I'll talk about how to debug afterwards. The next solution I moved to was this. So first we need to change our old script to work with making remote web calls. So to do that, we're going to set up a remote connection with the web service. Here I'm generating my ROP payload. You're going to see the ROP payload is a little different. I'll come back to that in a second. This is generating the actual payload that we're going to send, and then we send the request. So this is just standard HTTP. We're just doing it manually. So we're going to make a post request to that endpoint, the host, the content length, and then the body comes down here, and that's it. So like I said, if you make that, do those requests, and you send over that ROP code to spawn shell, I'm able to show in GDB, and I'll show how I do that in a second, that it does spawn a shell. But it's just, again, it's just not interactive. It closes real quick. Maybe I'm supposed to pass a -i to make it interactive and stay open. I just had a lot of trouble, and I just don't trust that the connection works and stays open over Apache. So I dropped doing that pretty quickly, and it ended up just writing ROP code to just read out the flag file. So I didn't spawn shell. I just write ROP code that reads the flag file and returns it over the HTTP connection. Let me actually... I think I need this one first. Yeah, we'll do this one first. To actually show how to debug it and show that prove to myself that I was spawning shell and something else weird was happening. This is just to show how to debug this. What I did was I did docker ps. So right now, actually a couple different things. So we're gonna do apt install Apache 2. So first I wanna get this running locally. Let me get the rest of the commands. So we're installing Apache within Ubuntu. Then I found some docs for enabling CGI. Very easy. Apparently this enables CGI, so good enough for me. We reinstall the Apache instance. We're going to copy it to the default CGI bin. Cool. And at this point, we can make requests to the local CGI. And cool. So we have a local version running that we can test with. If we want to run GDB, again, we need to run GDB on this process. I could probably do it within the same solve script. But what I ended up doing was just creating a second bin shell within that same container. So to attach to a container, you can do, like I said, docker ps. We get the container ID. We're going to do docker exec interactive this bin bash. And so now these are both running in the same container. So you can do a psaux, see what else is running, and we can see our first session right here. And here's the Apache. Cool. So at this point, I did pgrep. The process was called auth.cgi, I think. So we can see it's not running right now, but we're going to do a GDB process this. So pgrep will return the process ID of a process that matches this. We want the process ID. We're going to do a GDB, and we're going to attach it to that process while it's running. Cool. So we're going to run this, and we're going to put a sleep here. So what's going to happen is it's going to open up a connection, start the process, send the first, like all the headers and stuff to the auth.cgi, and then we're going to leave that connection open for 2 seconds before we send the payload. So the binary is running. We just haven't sent anything over standard in, so it's hung on that read call. Then we attach GDB, and so we can debug. I'm probably not connecting locally. There we go. Backing out, another mistake. I forgot to make the container privileged. Running it again. Cool. So now we have GDB open and we can actually debug it and see what's going on. So at this point, you just, you do your normal stuff. So finish, next. Here we're starting to execute the shellcode. This doesn't spawn shell. This actually reads the files, or I think it's reading the directories. But anyways, this is how I was able to debug it to prove to myself that I am spawning shell and things just weren't working. Again, maybe I'm supposed to do the -I for interactive. Maybe I'm just doing something else dumb. Very possible. But at this point, I gave up trying to spawn shell and I decided I'm just going to read the flag file. So to read the flag file, what I ended up doing was I wanted to use the syscall for get directory openings or get dents, which is here. Is this get dents? Yep. Oh, cool. So there's a syscall called get dents, get directory entries. At the time I did this, I don't think it was saying where the flag was located. So first I had to figure out where the flag was. And so to do this, similar to how I was writing bin shell to elf.bss, I was writing home. At first I wrote root to elf.bss using that same write what where gadget. And then I did you have to open that file. So I opened the root directory. I printed out, opened the root directory. Then I call get directory entries on that file descriptor. So that's file descriptor 3. Again, because I had GDB, I could test everything locally. And then I printed out, as part of the web request, the directory entries, so I could see all the files. From there, I saw that there was a home and a CTF, and so I was able to eventually find the flag file. But like I said, I started with that. Then I did, home. I did a zfill up to 8 bytes. And then I saw there was a CTF user. And then once I went into that directory, I saw the flag file. Once I knew where the flag file was, I ended up on the final script. Again, so I'm writing home, CTF, flag.txt. These all have to be 8 bytes because we're storing this content into a register and the registers are 8 bytes. So again, I'm using that write what where gadget so to write out home. And then you see I do elf.bss +8, then I write out flag and then .text. And then again, I open that flag file. I read from the flag file. So we're doing an open, read, write. If you saw, I just did a video on SecComp and we talk about this open, read, write pattern a little bit. But anyways, open, read, write. And then I just write back the flag to myself and that was it. So we're not writing shellcode to the stack or anything. We're just wrapping by reading a file and then writing out to standard in or to standard out, which eventually gets proxied back to the browser, which is just a solve script. But anyways, all that we can now run it. Hopefully that made sense. We can get rid of this one. So Python 3, it's solve web, and this is the open script. There we go. Involved challenge, but we finally got out the flag. CTF certified genuine instructions. So cool. That was the first one. The second one, we go back to Pwn. It says similar, but the stack is no longer executable. So I guess maybe this is the solution that I already did. But we take this URL. I'm just going to copy it in here because we're lazy. The same solve script should work. We'll put it right here, copy, paste, and we run the script again. And we can see it works for this one too, because we're just wrapping. We never wrote shellcode to the stack. So Computational Genius Institute. So sweet. So I haven't tried the third one. This came out after I stopped playing, but we can try and see if it works. It said something about crypto, and I haven't done any crypto stuff, so it seems unlikely this would work, but maybe it does. And we run it. Sadly, it does not work. The fact that we're getting an HTTP OK makes me think that maybe the password is XORed or something, so our shellcode is XORed. But we just have to open up the auth.cgi and take a look and see what's happening. But no free points. Next up is we have turning complete. We did Shinji as part of the mobile. So as turning complete, we built a Turing machine and put the flag onto the tape. Can you figure out how to work it and get the flag? Author Ron, and we're given a netcat port and a download file. And the download file is just a binary, so we can open that up in Ghidra. So for this, it's doing something, not too sure. It says flag.txt, so we got flag stream. Eventually, it's going to read from that onto some stack, OX 20 bytes. Cool. Then it's going to print out some binary. And then while it's going to call this R function a bunch, this R function just calls getChar. So presumably this R function is just grabbing a character. And then it's kind of entering a switch case statement. I think there's two. So I think there's a C1 and a C2. So there's like two different things it's reading in. But if we know a little bit about Turing machines, we know they're pretty simple machines. There's like a memory pointer, I think, and you can kind of increment it and decrement it. There's also a print function, I guess. And that's all we really care about. Somewhere on stack, there's the flag. We can increment a memory pointer and print out the contents there. And so we can see these kind of look like memory pointer operations. So here's increment and decrement. So we're just going to call this memory pointer. And this is printing out the contents of the memory pointer, that byte. And so we can see C1 needs to be 0 and C2 needs to be 1 to subtract, or 1 and 0 to add, or to print, and 0, 0 to add. So cool, sounds good. So we're just going to start printing and then incrementing and printing and incrementing, and we pray that the flag will print out. And if we write that into a shell script, it works. So that's all we really had to do. So we're going to send a p.send. This is the print command that we just saw. A 1 and then a 0. Then we receive 8 bytes. And this is just binary 1s and 0s, kind of like this. And then I print it, convert it from binary into an integer, add that to some dump variable, print out the dump, and then 0, 0 is increment. So then we move the memory pointer up by 1. And that was it. So we can run it, Python 3, solved.py. Wants to be in Docker. Although I don't even use it, but I guess we'll go into Docker, Python 3, solved.py. And it's building out. Hi, thanks for finding me. The flag is CTF RIP 1912, 1958. So I'm guessing that is the birth and death of Alan Turing, but fun challenge. Up next is the terminal challenges. First up is meow. It says terminal challenge, welcome, flag is located here, author Daniel Pendolinio. We're given a terminal or a web terminal or a netcat port. 413 solves. So this was the welcome challenge of the CTF, I guess. Welcome to BSides. I'm not kidding around. Just take a look to find the flag. We're CTF, home directory. We can do an ls. We see a flag. We cat it out and we get the flag. It says CTF cannot stop meow. Fun. The next challenge is no tools. It says the flag is here, but where'd all the tools go? And same as last time, we're given a netcat port or a web netcat port. So if we connect to it, it turns out my solution is no longer working. So I'm not sure what that's about. Maybe the solution I used, I'm wondering if someone was storing the flag. Oh, I copied it up here. You can see I'm trying a whole bunch of stuff. This is what I was doing. So I was reading into the variable a 100 bytes from flag.txt, and it printed out where are my tools, bad variable name. I thought this was working, but now I'm realizing maybe someone was storing the flag in the variable a, and somehow I got access to that, or the challenge is now broken. I'm not really sure. So when I run it, I just get bad variable name. I tried a bunch of other stuff, like you can see here. I thought these would work, but having trouble with this too, or echo. Although that's working. If you do a file name that doesn't exist though, it gets upset. So I'm not too sure what's going on. Yeah, I guess I just got lucky and someone else was storing the flag as $A and I thought I solved it and maybe I didn't. So I'm excited to see the write it from someone else. And the last category is web. The first challenge is match 1. It says match cards to win, don't get any wrong. The author is It's Corgi. So for this challenge, first you register an account, then you sign in. And so for this, we're just supposed to match all the cards, but you can't see the cards, so it should be impossible, but we're hackers. So first step, we look at page source. When you look at the page source, this might be a little hard to see, but you can see these are all the different cards, and it has a data value of 4, data value of 3, data value of 8, 2, blah, blah, blah. And if you look at these, they correspond to the shape. So the solution was just take all those numbers and put them in a grid, and just write it down. I mean, I guess you don't have to write it down. You can do it manually, but it's easier if you write it down and then you just match the numbers and that's it. So we already have the answer. It was embedded in source code. You just need to copy it out. So if we take are the two close by? 8 and 8, so the bottom two. So we take this one and this one, we can see they match, and because we both knew they were 8s. But anyways, do that for all of them and you get the flag. The next 3 challenges are web tutorial 1, 2, and 3. So for each of these, we're just given a website. So if we go to the website, the hints I think are pretty necessary to solve the challenge. It says you need an XSS payload that bypasses the following CSP. We can see we have unsafe inline here, so we just have generic XSS injection or JavaScript injection. It says notice that the unsafe inline is allowed. Try inserting this, blah, blah, blah. It works. And here only the admins can view XSS 1 flag. So we need to steal it from the admin session and send it to ourselves. Cool. And then it tells us to do 2 sessions, blah, blah, blah. So for this, we just need to read from that endpoint and send it to ourselves. So this is what my payload look like. We're going to fetch from XSS1 flag, convert it to text. And then once we have the flag, we're going to send a request to webhooks.site with the contents of that, that fetch call. So we send it here. We're going to put this in a script tag, close the script tag. We submit it, so now the admin bot sees it, and we get 2 webhooks, so cool. The first one says CTF, try some XSS. So cool. We solved the first one. For the second one, cool. The first hint, we can see script source, self-random nonce. So we no longer have just generic injection. And what else? Default source self. Cool. Then we have hint 2. Notice the unsafe inline is no longer allowed. You can no longer insert script tags, so we need some way to bypass the CSP. It says XSS to result is sourcing JavaScript from woof.js. Can you trick the page to use your file instead? So when I saw this, I thought we were supposed to, like, there was a JSON-P endpoint on woof.js. So I spent a bit of time like searching through here. Very confusing how this was related. I assumed it was a JSON-P, but I hadn't seen the CSP. And it's weird, maybe the random nonce and they forgot like a strict dynamic or something, which is like a more advanced CSP feature, but it turns out it's way simpler than that. If you just go to this page, we can see that it is literally just making a request to woof.js. We can see here, failed to execute script. And if we view the page source, woof.js, we can see it's just loading this woof.js, but there's no path or anything like right there. And we can see the nonce is here. And it's a valid CSP nonce. It changes every time. So most likely we can't guess the CSP nonce to inject our own script. But there's a CSP attack related to that called, I guess, a base href attack. Basically, you can specify an element. I'll just put it down here. Base href is equal to something like this. And what this will do is this will specify the, I guess, kind of like the base origin for all, I guess, relative path offsets. That might not be the right word, but since woof.js was just loaded like this, if we specify a base of Conrad, instead of loading it from just like slash or like the web origin, it'll load this from conrad.io, and it should be like attacker.com or whatever. But if we control this endpoint, then obviously it'll load our JavaScript. It'll have a valid CSP nonce, and so it'll be executed. So to actually do that, we're going to go to tutorial 2, notes. We're going to write our own woof.js. Cool. We then need 2 web servers. So we need a public-facing web server and one that's running locally. So we're going to go tutorial 2. We're going to go Python 3, HTTP server. Then we're going to open up an ngrok. We do ngrok HTTP 8000. So this is setting up a local web server, and this is poking the hole. So now we can access woof.js right here. So here we have woof.js, and it's publicly accessible. From here, we're going to change our base ref to our ngrok URL. So we want this. This is our new ngrok. We're going to place it here. This is our base href attack. So we're going to send this. This is going to get injected as HTML into the next document. And then when it loads, that page loads woof.js as admin bot, it'll instead load the woof.js from our ngrok, which goes to our local web server, which then loads this payload. This payload's pretty much the same. It's just going to load XSS2 flag because we're on the second challenge, and then send that to a webhook site. Cool. So not flag. We go back. Here's our base href. We send this over, and we hope, we close the webhook site. but we hope we get some new webhooks, and there we go. CTF, all base belong to us. So it was a base href attack. And then for the third challenge, let's go back. We want only web, web tutorial 3. I thought the third one was easier than the second one, but it could just be me. It says, notice unsafe inline is no longer allowed, but there is a wildcard. Try to do something with data URIs. Hint 3, it doesn't say anything new. So, and I missed a hint 1. So script, we can do either self or data. Data works for us. That just means do an inline data base64 injection. So not too bad. So this is what the payload looks like. You take the payload. It's the same payload that we've used a bunch of other times, except it should be fetch 3 flag. Not sure why that worked. Then we take this payload. I think I was doing it in CyberChef, that's why. And this is how you can specify a script data source. So we're doing script data. It is application JavaScript, but it is encoded with base64. And this is just a generic alert payload. So we're going to replace that with our payload, which is just this. So you take it to CyberChef, you base64 it, and you put it in where the base64 was. And we grab it. We place it here. We hit enter. We go back to the webhook. We have new webhooks. And there we go. CTF data URIs are back. So fun. And that is all the challenges I solved. So yeah, like I said, it was a very fun CTF, good difficulty curve. The challenges were fun. And I can't believe how many challenges there were. 50 is a lot, but yeah, good time. Monday, I have a video coming out on CSP WebRTC bypass. So that should be Monday morning at some point. And then I'll have a couple more of the security topic videos coming out at some point next week too. But yeah, thanks for watching. I'll see you at the next CTF. Cheers.